So in the previous class, we have studied the working of a solid state laser when it is pumped with a single diode laser through one of its ends, as you can see here. The best example of an end pumped solid state laser is a green laser, one of the popular example. Basically, it is the most common example of an end pumped solid state laser which operates as a green laser pointer that emits at a wavelength of 532 nanometer. Let me just explain the operation of such an end pumped green laser. The 808 nanometer infrared emission of a gallium aluminum arsenide diode laser usually pumps a neodymium doped young laser that we know emits quite deep in the infrared at 1064 nanometer wavelength. So basically you have the ND-YAG pumped, ND-YAG doped solid state laser. Then you pump it, this is your diode laser. Diode laser operates at 808 nanometer and it pumps it the way we have already described before, and then it emits at 1064 nanometer wavelength. Then you actually, this 1064 nanometer light is then frequency doubled in a nonlinear crystal producing green light at 532 nanometer. This is a nonlinear crystal. You shine this light to a nonlinear crystal and it actually frequency double. That is called second harmonic generation. This is a nonlinear process by which you can actually convert light at one frequency into light at another frequency. Unfortunately, this is I cannot explain the underlying physics here, which is actually outside the scope of this course. But accept it that such a nonlinear crystal can frequency double this light, 1064 nanometer wavelength. If it is frequency doubled, then its wavelength will be halved. So wavelength will be 532 nanometer, which is green. So this is a diode pumped green laser. Basically you have two different components. One is the solid state laser, which emits at 1064. Then there is a nonlinear crystal which frequency doubles this 1064 nanometer to the green light. And the overall efficiency of the infrared, this is infrared and this is green. Infrared to green conversion efficiency can be as large as 20%. That means if your diode laser gives you a power of output of 1 watt, you will produce green light. If you can obtain this kind of conversion efficiency, you will generate 200 milliwatt of green light. However, there are some limitations of end pumping, and let us just see what are they. And we will also try to understand the need for side pumping that is possible with multiple diodes. Why do you need that? You see, the pump can be introduced here from at most two directions. Basically, the two ends of the rod. You have the rod, and we just studied, this is your diode laser, coupling the diode emission through one end of the rod. You can at most increase the pump energy by putting another diode on the other end. So if you have to generate higher power from this, that means you'll have to increase the pump energy. You can just at most double this pump energy by putting a second diode and coupling this emission of the second diode through the other end, and that is all. You can't go more than that. You have only two ends. The N coupling schemes are thus suitable for modest to moderate power solid state lasers up to just several watts, few watts. That's all. Probably you cannot go even to 10 watt. No. The pump power required for the operation of lasers with higher power cannot be provided by one or two diodes alone. You need more number of diodes. That is, you have to increase the pumping energy if you have to generate more power from your laser. Moderate to high power solid state lasers are required to be pumped by multiple diodes, multiple diode emitters. These lasers are essentially pumped through the sides, and if you have multiple diode lasers, so you have to definitely pump them from side. You have to use many diodes and pump them from the sides. And depending on the requirement of the power, they can be pumped either by diode bar or a diode array. Let us see what is a diode bar and what is a diode array. You see, diode bar comprises a single row of closely spaced laser diode emitters. For instance, it would be like that. Suppose these are our diode lasers. So, closely spaced diode lasers in a single row. So this is a diode bar. And how a diode array would look? Diode array consists of multiple individual laser diodes arranged in a specific pattern, often in a two-dimensional grid. Suppose you need to increase the energy that needs to be pumped into the laser rod. So you need more diodes. Diode bar will give you such a would basically would look like this. And a single row, you have to just put your diodes closely spaced one after the other. And diode array, it is shown, so in two dimension, you will have so this would be the diode array. You can actually put many more diodes into this array than what would be possible in case of a diode bar. So you can essentially think that diode array is a number of diode bars which are combined together. So how do you use this diode bar or diode array in the operation of a laser? You have to, of course, pump them by the side. For example, you see, if you use this diode bar to pump your solid state device, solid state medium, then this is your rod, and each of these diode will emit its light, and this is the beam of light which you would couple into the lasing. And therefore you see, you can pump much more energy. Each of these diodes would probably give as much energy as in this case, Now you have used so many of them. So you can really use the pump power, and you can make the solid state laser emit much higher power. So how do you use them? So this is the experimental, very schematically shown, and a qualitative way that is shown here as to how a side or transverse pumping with multiple diodes will work. So this is your active medium, is the rod into which your atoms are doped, and this is the diode bar. That means there are many diodes placed one after the other. And these are the emission of the diode, which has been coupled with some appropriate optical element which has not been shown here, in such a way that you have very good pumping, so, homogeneous pumping of the entire medium, active medium. And this is the top view. You can see there is one diode bar at the top and one diode bar in the bottom. But actually you can have multiple such diode bars placed all around this laser rod. Now this is the top view and this is the end view. In the end view you can see there are actually four diodes. These two are near these two, and these two are actually in the front and behind. So here you can see that this is being pumped by such four diode bars, and you can have more diode bars actually. For example, in this case you have 8 of them all around to increase the pump energy. So the emission from the pump diodes is made to shine on the laser rod here from the sides. The host crystal is surrounded by the coolant. This is the coolant tube, jacket, which is wound around this laser rod. This is the end view. That flows through the outer glass tube. This is the outer glass tube. And the outer surface of the rod. It flows through the outer glass tube and the outer surface, this is the rod, the outer surface of the rod, to remove the heat that is rapidly conducted by this rod onto its surface. With this arrangement, of side pumping, it is readily possible to pump a laser rod with several diode bars, each with an emitting region matching closely to the length of the rod. So each of these diode bars, with an emitting region matching closely to the length of the rod to enhance the efficacy of pumping. And the major advantage of side pumping is that the gain, unlike the case with end pumping, remains homogeneous across the length of the rod. I think you will be able to appreciate this point if I tell you a little bit more about pumping a laser rod through one of its end by a diode. See, the diode laser, it is being introduced to the rod through one of its end. Now you have the absorbing atoms here, they are embedded here into this. Now as this pump beam enters, at the entrance its intensity is maximum, and as it keeps moving, its intensity keeps on reducing because these atoms are absorbing photons from this beam. So as it travels, if its intensity, this pump's intensity were I0 here, then as it travels, its intensity, if it were I0, it will drop slowly, gradually. Because now photons are being absorbed. So less and less number of photons would be available for pumping as it travels further and further into the rod. And if there are lesser and lesser photons are available, so the gain that will be created also will be lower and lower. So if you plot the gain as a function of the length of this rod, at the entrance gain will be maximum. This is gain. So gain will be maximum at the entrance, and then it will gradually drop as the intensity of the beam drops. So the gain would not be homogeneous in case of pumping through one end. Of course, you may say that we pump it from the other end. Then of course there may be some compensation and gain may not look as bad. But consider now this case. This pumping is absolutely homogeneous because you are using multiple diodes. So the gain remains homogeneous across the length of the rod. And the lasers capable of delivering tens of watts of several or to several hundreds of watts can be pumped by diode bars, while the kilowatt class lasers require diode arrays as the pump source. If you have to obtain kilowatts of power, then the laser needs to be pumped by diode arrays, the number of diode arrays. While if you have to obtain tens of watts to hundreds of watts, tens of watts to hundreds of watts, diode bar, and kilowatt class of laser, diode array. Alright, now let us quickly turn our attention to continuously tunable solid state lasers. You see, solid state lasers essentially is a transition between discrete electronic energy levels, and therefore the light that is emitted is also at discrete wavelengths. So solid state laser normally gives you coherent light at discrete wavelengths. Discrete wavelengths. However, in some solid state lasers, a very strong interaction between the doped atoms and the host crystal results in an intense coupling of the electronic energy levels with lattice vibration. Basically, the phonon electronic interaction reduces the lifetime of the corresponding energy level. You see, the lattice vibration. What is an acoustic photon? An acoustic photon is a quantum of atomic lattice vibration that essentially represents a quantum of sound, like the photon, which is actually a quantum of light. Now, the strong coupling between this energy, electronic energy levels and lattice vibration basically provides a channel for the energy to flow through creation of acoustic phonons by way of exciting vibrations of lattice. As a consequence of Heisenberg's uncertainty principle, both the originating and terminating electron levels are therefore broadened. If the lifetime reduces, the energy levels are broadened. This thus gives rise to the prospect of tuning the wavelength of these lasers across a range determined by the width of such broadening of the levels. As tunability arises from the interplay between lattice vibrations and electronic transitions, these lasers are often called vibronic lasers. The mechanism of the tunability is fundamentally similar to that of the electronic transition of a dye laser that originate from optical phonon. You see, the energy of a vibrating molecule, it is not vibrating molecule, it is the atoms which make up the molecule, they actually vibrate and also rotate, and these energy levels are quantized. And a quantum of energy is equivalent to an optical phonon. Like here it is acoustic phonon, there it is optical phonon. But the mechanism is same of the broadening. So this is the incident pump light excites the atom from the ground state to the pump band, from where they drop down to the upper laser level. That basically is a vibronic band. So this is your ground state. Once again, we are considering something similar to ND doped neodymium doped YAG laser. but not quite, because that would not give such vibronic bonds, vibronic bands. So the mechanism has been represented in this low-lying energy levels which participate in the process of lasing. Once this upper vibronic band, once these atoms relax to the upper vibronic band, they relax very fast to the lowest energy point of this band. So they quickly come to the lowest energy state, that is here, of this vibronic band, upper vibronic band. The lasing transition originates from here and terminates at any location on this. It can terminate here, it can terminate here, it can terminate here, it can terminate here, and like that. At any energy location within the lower laser level of the vibronic bond. However, there is some catch here. The lowest energy state of this band, by virtue of being nearest to the ground state, this is the ground state, we will have some thermal population. And the lowest ground state, that is this, will have the maximum thermal population. And the population of this band will be distributed following a Boltzmann distribution. As you go up in the energy, the population will reduce. And therefore, between which transitions the population inversion will be maximum? The highest energy state in this band will understandably have the least population. Therefore, this band will have the least population. And this state, energy state in this vibronic band will have the maximum population. Therefore, the gain will be maximum for this transition and minimum for this transition. Now this transition will give the shortest wavelength. See, lambda, this will be the shortest, and this will give lambda, which is the longest, and this is the shortest. So the laser gain will decrease with decreasing wavelength. So for this wavelength, shortest wavelength, the gain will be minimum, because here the population inversion is minimum. So if you plot gain and wavelength, so gain will be minimum for short wavelength and maximum for long wavelength. So as the lambda increases, the gain increases. Thus, in a non-dispersive optical cavity, if the cavity is non-dispersive, lasing will predominantly occur at longer wavelengths. So if there is no dispersive element in the cavity, then lasing will predominantly occur at the wavelength for which gain is maximum. Absolutely fine. And the optical arrangement to realize the tuning of the wavelength is qualitatively similar to that used for CO2 and dye lasers. It makes use of a diffraction grating, and the mechanism of using grating to tune the wavelength of the laser will be discussed when you study carbon dioxide laser. So if you do not use a dispersive element, then the emission will be predominantly at predominantly at longer wavelength, where the gain is more. Among the vibronic lasers in operation, today the titanium sapphire laser offers the widest tunability, covering an incredible range of red, that is 600 nanometer, to well into infrared 1180 nanometer of the electromagnetic spectrum, very wide. The extremely strong interaction that titanium exhibits with the host sapphire crystal has made this possible. Here the interaction between the electronic energy state level and the lattice vibration is extremely strong. That's why the broadening also is that much longer, that much more. Now, the titanium sapphire laser was first operated in 1986, and its growing popularity soon pushed the dye lasers, once ubiquitous in applications requiring a tunable laser, into oblivion, because a single dye laser would not give you such enormous tunability. You know that the dye laser, you have already studied dye laser, you know that dye laser, the maximum tunability that you can obtain is that rhodamine 6G, which gives a maximum tunability of 80 nanometer. Compare this 650 to 1190, 1180. So 430 nanometer is the tunability of rhodamine, so of this titanium sapphire laser. That's why it has put dye laser into almost oblivion. Now it is appropriate to present here a brief description of the operation of titanium sapphire laser. So the construction operation of titanium sapphire laser is quite similar to other kind of solid state lasers. This is the lasing rod, where sapphire is the host, and into which titanium, the light emitting species, have been doped. However, it cannot be pumped by diode laser because titanium can be pumped around 500 nanometer, but at this wavelength a good diode laser does not exist, so it cannot be pumped by a diode laser. So how it is pumped? The absorption of sapphire laser peaks at around 500 nanometer, which an appropriate diode laser is not readily available for which. So how it is pumped? The second harmonic of Nd:YAG laser, which is at 530 nanometer. You have seen that 1064 is the Nd:YAG output. Nd:YAG lasers are that. So you put a nonlinear crystal, and that will frequency W and give you 532 nanometers. This green light, Nd:YAG laser, 4064 nanometer, second harmonic generation crystal, converts into 532 nanometer, which will pump it, couple it through a dichroic mirror, which transmits 530 nanometer into the lasing medium, and you achieve pumping, because it can be pumped at around 500 nanometers, so it is very close to the pumping wavelength. Although argon ion laser, it operates at 514 nanometer, you have seen. This is also an efficient wavelength for pumping titanium sapphire. It also finds application as a pump source here, but it has not gained popularity, largely because of its poor operating efficiency. You know that argon ion laser operates at about 0.01% efficiency, which is very, very small, and therefore it will have exorbitantly high running cost because of its such very low operating efficiency. The cavity of this laser can be formed between this is the dichroic mirror, and a concave output mirror, which has been shown here. This dichroic mirror will transmit 532 nanometer but offer very high reflectivity at this wavelength at which this will lace. That is the wavelength between 650 nanometer and 1180 nanometer. So you specially fabricate such dichroic mirror. The tuning element, that is the dispersive element to tune this, has not been shown here. Now the wide tunability of titanium sapphire laser can be readily translated through nonlinear generation of higher harmonics into shorter wavelengths, covering a broad range of spectra from blue to UV and even beyond. For example, you see, if the titanium sapphire works at say around 650 nanometer, 680 nanometer, say. So if you frequency double it, you put a nonlinear crystal, so it will be 340 nanometer. It is well into the UV. And you 340 nanometer, you again frequency double. You will generate 170 nanometer, which is almost the vacuum ultraviolet region. So that's what the wide tunability of titanium sapphire laser can be readily translated through nonlinear generation of higher harmonics into shorter wavelengths, covering a broad range of spectrum from blue to ultraviolet and well beyond. And further, the ultra-wide tunability of titanium sapphire laser also allows the generation of ultra-short pulses from these lasers by employing well-established techniques. However, this is beyond the scope of this course, so it won't be possible for me to explain here the underlying physics of generation of such short pulses. But this brings an end to our course on operation of solid state lasers and also both discretely tunable, both solid state laser that gives coherent light at discrete wavelengths as well as coherent light at continuously tunable wavelengths. All right, let me end here today.